Module 2, Physical Layer Mastery, RS232 and RS485, where noise kills data. Now we stop talking philosophy and start talking physics. Up till now, everything we discussed could live happily on a whiteboard. From here onward, electrons, ground potentials, motors, VFDs, and bad earthing enter the room. And once they do, noise becomes the real boss. This module is about understanding why some links survive plant floors and others die quietly at commissioning. Balanced versus unbalanced signaling. Why differential always wins in industry. Let me say this up front, very clearly, the way experience teaches it. Most communication failures in plants are not problems. They are physical layer misunderstandings. And at the heart of that misunderstanding is one concept engineers underestimate early on. Common mode voltage. Unbalanced signaling. RS232's hidden fragility. RS232 is an unbalanced system. That means one conductor carries the signal, another conductor acts as a common reference, signal ground. The receiver interprets data as the voltage between the signal wire and ground impulse. In a laboratory, it's fine. In a plant, this is where trouble starts, because now your communication depends on ground behaving nicely. And ground, in industrial environments, rarely does. Motors start, contactors drop, welders fire, VFDs scream harmonics into everything nearby. All of that energy couples into ground. The result? The signal voltage you think you're transmitting is no longer the voltage the receiver sees. That difference is called common mode voltage, and once it grows beyond tolerance, data corruption becomes inevitable. RS232 doesn't fails intermittently, and intermittent failures are the most expensive kind. Tash-balanced differential signaling, RS485's superpower. RS485 takes a completely different philosophical stance. Instead of asking, what is the voltage relative to ground, it asks, what is the voltage difference between two wires? Two conductors carry complementary signals. The receiver ignores absolute voltage levels and focuses only on the difference between them. This single design decision changes Eve ice hits. Both conductors are affected almost equally. The noise becomes common to both. The differential voltage, the actual data, remains intact. Noise doesn't disappear, it just stops mattering. That's why RS485 is described as a balanced or differential system and why it supports longer distances, higher data rates, far better noise immunity. The silent saboteur hears they to internalize. Noise doesn't usually attack your signal directly, it attacks your reference. In unbalanced systems, reference equals ground. In balanced systems, reference equals the other conductor. That's why balanced signaling is fundamentally more robust. RS485 doesn't assume ground is clean. It assumes ground is hostile and designs around it. That assumption alone makes it plant-worthy. Why differential signaling dominates plant floors? Look around any industrial site and you'll see the same pattern repeated. Long cable runs, shared trays, high EMI environments, multiple power supplies, different earth potentials. RS485 was built for this chaos. It supports multi-drop networks, long distances up to kilometers, high noise environments, controlled contention through tri-state drivers. RS232 was built for short distances, point-to-point links, clean electrical is good or bad. They are honest about the environments they were designed for. The physical layer truth. Most engineers learn late. If you remember only one thing from this section, let it be this. Protocols don't survive noise, physics does. Differential signaling wins not because it's clever, but because it refuses to trust ground. That mindset, distrust the environment, is the same mindset that separates hobby communication from industrial communication. And now that you understand how signals actually survive copper, the next step is inevitable. Once multiple devices share the same pair of wires, who gets to talk and when? That's where RS485 becomes even more interesting. Hashtag RS232 in the real world, why it works on my desk, fails in the field. Let's talk honestly now, because RS232 is one of those technologies engineers think they understand right up until it embarrasses them during commissioning. On your desk, RS232 behaves like a gentleman. In the plant, it behaves like a liability. And the reason has nothing to do with software skill. It has everything to do with physical assumptions. DTE and DCE. The first trap you fall into, RS232 was never designed for industrial control. That's not an insult, it's historical fact. Its original purpose was very specific. communication between data terminal equipment DTE and data circuit terminating equipment DCE. Think computers talking to modems as this strange wiring logic. DTE transmits on one pin, DCE transmits on the opposite pin. Ground is shared and assumed stable. On your desk with one PC, one device, one power source, one earth reference. This assumption holds. In a plant, it quietly collapses. You end up with two DTEs facing each other, or two DCEs, or mismatched expectations about who talks on which pin. Hence the infamous null modem cable hacks that feel more like rituals than engineering. RS232 works until roles aren't perfectly respected. Point-to-point means exactly that. RS232 is strictly point-to-point. One transmitter, one receiver, no sharing, no listening audience. The standard was never meant for networks, multi-drops, or distributed systems. The moment you try ICE, parallel a connection, tap the line, you're violating the electrical assumptions of the interface. And unlike higher-level protocols, RS232 has no polite way of telling you that you've crossed the line. It just starts misbehaving. Distance and speed, the lie of the spec sheet. Here's where desk success becomes field failure. RS232 is unbalanced, single-ended, ground-referenced. That means its reliable operation depends on clean ground, short cables, low noise. The tutorial is very clear here. Practical distance about 50 feet, standard data rates around 20 kbps, though higher is possible in ideal conditions. Now compare that to a plant and add cable tra-long, motors injecting noise, different earth potentials between panels. RS232 doesn't degrade gracefully. It crosses a threshold and then fails spectacularly and intermittently. And intermittent failures don't point to wiring immediately. They waste days. Hash voltage levels, another hidden assumption. RS232 uses large voltage swings. Logic 1, minus 3 volts to minus 25 volts. Logic 0, plus 3V to plus 25 volts. Those levels were meant to overcome noise in early telecom on an industrial EMI. Ironically, those large swings increase susceptibility to ground shifts, increase stress on interfaces, increase failure modes when grounds float. Again, it works beautifully when ground is well behaved. Plants are not well behaved. Why engineers keep falling for RS232? Here's the pattern I see over and over. On the desk, laptop analyzer, short cable, same power strip, clean earth. Everything works. Then the same setup is moved 40 meters away, separate panel, different power source, shared tray with VFD cables. Suddenly, random timeouts, garbled characters, unreproducible faults. Nothing changed logically. Everything changed electrically. RS232 didn't betray you. It simply did exactly what it was designed to do in an environment it was never designed for. That's the engineering takeaway you should internalize. RS232 is not bad. It is honest. It assumes one device, one cable, one ground, one quiet environment. The moment any of those assumptions break, RS232 stops being engineering and starts being hope. This is precisely why industry moved toward balanced, differential multi-drop systems. And once you understand this, RS485 no longer feels like an upgrade. It feels like survival logic. That's exactly where we're headed next. RS485, multi-drop reality, discipline on the wire. This is where industrial communication stops being a cable between two boxes and becomes a system. RS485 is not just RS232 with better noise immunity. It is a behavioral contract between multiple devices sharing the same physical medium. And if you violate that contract, the wire turns into a battlefield. Multi-drop, one pair, many devices. RS485 was designed for a truth RS232 could never accept. Open quote, more than two devices must share the same line. Close quote, electrically RS485 allows multiple transmitters, multiple receivers, long distances, high noise environments. Only works because of one crucial invention. Tri-state drivers. The hidden genius RS485 line drivers operate in three states. Logic 1, logic 0, high impedance, disconnected. That third state is EDANCE, means I am electrically invisible right now. When a device is not transmitting, it removes itself from the bus. No loading, no contention, no distortion. This is what makes multi-drop possible. Without tri-state behavior, every connected device would fight for control of the voltage and the bus would collapse instantly. Only one talker at a time. Non-negotiable law RS485 does not forgive simultaneous transmitters. If two devices talk at once, differential voltages collide, data corrupts, hardware stress increases, communication becomes undefined. That's why every RS485 system must enforce discipline at the protocol level. One talker. Everyone else listens. This is why master-slave architectures dominate RS485 networks. It's not a software preference, it's a physical necessity. The hardware allows multi-drop. The protocol prevents CAD. Had 2-wire versus 4-wire, half-duplex versus controlled duplex. RS485 supports 2 wiring philosophies and each reflects a different control mindset. In a 2-wire system, the same pair is used for transmit and receive. Devices take turns talking. Communication is half-duplex. This is the most common industrial implementation because it uses less copper, simplifies installation, forces clean turn-taking. In a 4-wire system, one pair is dedicated to transmit, one pair is dedicated to receive. Communication behaves like full duplex, but only in one direction per role. Here, one node is always the master and others are always slaves. Slaves never hear each other. Only the avoids accidental contention entirely and is favored when reliability beats flexibility. Termination, where most RS485 systems are quietly broken. Let's talk about termination, because this is where theory and practice part ways. RS485 lines have a characteristic impedance, typically around 100 to 120 ohms. When signals reach the end of the line and are not absorbed, they reflect. Reflections distort edges. Distorted edges create false bits. That's why termination resistors are placed at both physical ends of the bus, not at every device, not in the middle, only at the ends. This is not optional. This is signal integrity. One misplaced a healthy system behave like it's haunted. The discipline RS485 demands, RS485 gives you distance, noise immunity, scalability. In return, it demands strict control of who transmits, correct termination, respect for topology, thoughtful protocol design. It is forgiving of electrical abuse, but ruthless toward behavioral mistakes. The mental model to carry forward. RS232 asks, can these two devices talk? RS485 asks, can all these devices behave? That's the shift. Once you understand RS485, you stop thinking in cables and start thinking in systems, shared resources, negotiated access, and enforced silence. And once that clicks, you're ready to climb out of the physical layer and ask a more dangerous question. Who decides when a device is allowed to speak? That's where access control and real network intelligence begins.